Calculus. My name is Curtis Brown, and I've got Steve Kokoska and Tom Dick with me. And tonight we are checking out, it is fundamental. The theorem, fundamental theorem of calculus is going to be the topic tonight. Looking forward to the great content that Steve and Tom have pulled together for us. I do have a couple of things just in normal. I'm looking for anything you guys have in the chat. Love to chat with you about questions and things. Students, teachers, if you have not yet downloaded the questions that we're going to be looking at tonight, those are available in the description. I'll put the link into the chat here in just a second. And then finally, teachers, if you stick around to the very end, I will have a link for professional development hours. You can email me and grab that. So here we go. Oh, and a question right away.
No.
Steve, before you've even got stuff to look at.
Yes.
We have from Ryan asks, what are some real world applications for the fundamental theorem of calculus? Real world.
That's a good one.
So I'll let you guys think on that as you guys get started thinking about and getting ready to show the content, and then we can maybe give Ryan some examples of real world applications for the FTC.
Okay. Thank you, Curtis. All right, I think I've got my screen up there. It's great to be back with you and Tom once again. I sincerely hope, Curtis, that you've completed your homework tonight because, boy, we've got some good questions for you. This is one of my favorite topics to talk about. The fundamental theorem of calculus, the most important idea in the whole course. The fundamental theorem of calculus connects the two most important parts of calculus, differential and integral calculus. And we're going to talk about both parts, and I'm going to start out with one of my favorite types of questions, which you might use in class to help students actually discover at least the first part of the fundamental theorem of calculus. So here we have the graph of a function y equal f of x as shown in this figure. And let me just step aside for a second. You know, in many of the presentations that Tom and I have done with you, Curtis, Tom has talked a lot about using the TI-84 and defining a piecewise function or a piecewise defined function in the calculator. And this is kind of a backwards sort of a problem. Can you take this graph and could you actually define that function on the TI-84 and reproduce that on the graph screen? So I think that's just one good quick question to get started. Tom's talked about that in the past. And you know, for AP pre-calculus teachers, that's kind of a good question. It's kind of one of Tom's Jeopardy questions. Can you work backwards and reproduce the formula to get that graph? Well, all right, that's the function f, and we've defined this function g as sort of a definite integral. And our AP calculus teachers out there sort of know a little bit about where we're heading with this. They know what the fundamental theorem of calculus says about g prime, but bear with me as I work through this. So let's evaluate this function g for z equal to 0, 1, 2, 3, all the way up to 10. Let me see if I can arrow up here just a little bit. Curtis, forgive me here in consideration of saving just a little bit of time. I did not create a screen for every single one of these values, these z values. I think of this g of x, especially if f is positive. I think of this g of x as an area so far function. And we often see problems on the AP Calculus exam in which students have to actually evaluate a function like this. I'm going to do a couple of them, Curtis, and then we'll leave the rest for people to fill out this table here as I've got it on the left-hand side. I'm going to scribble a little bit down at the bottom here. I'm going to do the easy one first. G of 0 is just the integral from 0 to 0 of f of t dt, and that's certainly equal to 0. We know that if the upper bound and the lower bound are the same, that definite integral is just plain 0. Let's take a look at g of 1. Well, that's the integral from 0 to 1 of f of t dt. And visually or graphically, we have to go over here to x equal 1, and we have to find the area bounded by the graph of f and the x-axis. Well, that area is 2, but the graph of f is below the x-axis, and so that value is just a -2. All right, so I'm going to proceed through and jump through all of these, and you can see here as I reach a value of like g of 4, I've got some values, pardon me, I've got some area over here. We'll attach a negative sign to it, some area over here, which is positive, and I think that turns out actually to be a half, to be 0.5. So good. I'll leave you to check some of those for me, Curtis. Well, actually, I know you've done that already. But we're going to hold this table on the left-hand side sort of aside, and we'll come back to this. We're going to need a couple of values from that table in just a little bit. This is a really nice exercise, I think, again, to work through and to discover what this fundamental theorem of calculus part 1 is going to tell us. So here's my area so far function, and I've developed this table. Let's see if we can answer a couple of other questions associated with this function g and with this graph. So I've reproduced the graph up above. On what intervals is the function g increasing, or where is it decreasing? Well, we know that g prime of x is equal to f of x. That's true by the fundamental theorem of calculus. So I've got some problems here in number 1 sort of mixed in here, okay? Forgive me about that, but we know that the fundamental theorem of calculus tells us that g prime of x is equal to f of x. So the first thing I'm going to do is I'm going to take a look and see where is g prime of x, which is equal to f of x. Where is that greater than 0? Well, it's greater than 0 on this interval 2 to 7. It's greater than 0 on that interval 2 to 7. That means that g is increasing on the closed interval 2 to 7. Where's g decreasing? Well, on the interval 0 to 2, and then 7 to 10, f of x is negative. And so we know that g is decreasing on the closed interval 0 to 2 and 7 to 10. Now, we've talked an awful lot about this before, Curtis. We've talked an awful lot about should we include the endpoints in intervals and where a function is increasing and where it is decreasing. And it seems kind of funny to have this value, say 2 and 7 in both of these intervals, but that's okay. And we won't go into this in gory detail, but the reason for that is because a function is increasing on an interval, not at a value. And because of the strict definition, we can include a value in both of those intervals. Now, on the AP Calculus exam in general, they will not dock you, they will not take off a point if you use an open interval or a closed interval, unless the function is undefined there, unless there's something crazy going on there. But for me, in my class, for most of us, a function is increasing on that closed interval 2 to 7, decreasing on those two closed intervals. Okay. On what intervals is the function g concave up or concave down? Well, we have to see where g prime of x equal to f of x is increasing. Where is it increasing? Well, let's see. It's increasing, let's see, from 1 all the way up to 5, and increasing again from 8 to 10. Son of a gun, Curtis, these intervals are open. Why is that? Well, again, back to definition. A function is concave up or concave down at a value because the definition is given in terms of a tangent line, and whether or not the function lies above or below the tangent line in a neighborhood of that value. So for me, by definition, it's certainly okay to say a function is concave up or concave down at a value, and therefore I would not include 1 or 5 in these endpoints. And the reason is because there is no concavity at 1, there is no concavity at 5. G is concave down with the first derivative, with the second derivative is negative, where f is decreasing, and I think that if I got that right, it's on 5 to 8. Beautiful. Now, there's one other little detail here in this problem. Curtis, help me with this a little bit. What the heck is going on over here between 0 and 1? What's going on between 0 and 1 in regards to concavity?
In regards to concavity?
Yeah, in regards to concavity. And I'm going to scribble a little bit while you're thinking about this. This is
Yeah, scribble a little bit
G
because
prime. G prime is equal to f of x. So that's
sure.
the derivative of G.
We're looking at G.
G
Uh,
prime. So what does that say, Curtis? I'm going to try the Socratic method on you here.
try.
All right. So what does that say about f prime or G double prime of x on that interval 0 to 1? What would that be equal to?
So wait, I need to back off just a second. The picture we're looking at is G prime, or the picture we're looking at is G?
The picture we're looking at is G prime,
The picture we're looking at is G prime. Okay.
correct? So if I want to know what
So
G double prime is,
G double prime
would be f prime of x.
would be F
What's f prime of x in the interval 0 to 1?
0.
Correct. Therefore, what's the concavity of G on the interval 0 to 1?
I don't I don't remember. Steve.
Well,
Zero.
if the second derivative is
The second
0,
derivative is 0. There's no concavity. Like,
beautiful, perfect, Curtis. There's
okay. Well, I
no
was trying to, I was like, it's not concave up or down. So I'm
correct. It's
struggling with
not
that.
concave up or down. There is no concavity there. Good,
Thank
good,
you. And
good.
Mark says it's linear. That's, I was going to say something like that.
Oh,
I was
oh, wait a
feeling
minute.
very,
He said it's linear. What? He used a pronoun there? What's linear?
he just said linear. The
Ah,
concavity is linear.
well, no, we're not accepting that. So here's the next question. Something like
Mark, you're getting me in trouble here.
something like this occurred on the AP exam a year or two ago. So I'm going to do just a little bit of erasing. And the question is, Curtis, if there's no concavity in here, but let's see, we know that f prime is increasing, so it's concave up there. Is there a point of inflection there at that value where x is equal to 1?
Where x is equal to 1, is there a point of inflection?
Yes. Who knew there were so many good questions in here?
I wasn't planning on there being this many beautiful questions inside of
Is
it.
there a point of inflection there?
Well, we go from 0 to increasing,
Right?
but it's a sharp curve because it's a sharp curve. So I would say the F prime doesn't exist there, right? So I'd say no.
Okay. But what if, can you have a point of inflection? Let me rephrase that. Can you have a point of inflection where the second derivative does not exist?
You have a point of inflection where the second derivative does not exist. You're asking it in a way that I should see saying yes, but
Very
I
good.
don't,
Sometimes,
Very
sometimes.
good.
but I don't think I'd
Very-
say I'd say sometimes. That seems reasonable.
It is certainly possible. So what's happened in this function is this function g has gone from no concavity to concave up. What's a point of inflection where the graph changes from concave up to concave down or from concave down to concave up? It has not done that at x equal to 1, and therefore I would say there is no point of inflection there. So this created a little bit of, not controversy, but discussion on the AP exam a couple of years ago. And I don't think we're going to see another problem like this for a while because of that discussion. But make for a good discussion tomorrow morning at 8 o'clock. I like that one. Cool. There's more, Curtis. D. Can we find the absolute maximum value and the absolute minimum value of the function g on this interval 0 to 10? Well, how do we do that? The first thing we do is set out to find the critical values, the critical points of this function g. So where is g prime equal to f? Where is that equal to 0? I'm sorry that I did not really reproduce that graph in this part D, but it is kind of down below. If you can bear with me, it is 0 at x equal to 2 and x equal to 7. be careful. Are there any places where f prime of x does not exist, where g prime of x does not exist? No. Even though there are sharp corners in f, remember that's a graph of this derivative and it exists everywhere. So g prime of x, are there any places where it DNEs? None. So I'm going to use the table of values method. So I'm going to evaluate g at the endpoints, which were 0 and 10, and at these critical values 2 and 7. And this is where I'm going to go back to my table that we created back in part A. And if I've drawn those values back in here correctly, I think I can see that the absolute maximum value is at 8, and the absolute minimum value is, pardon me, the absolute maximum value is 8, and it occurs at x equals 7. And the absolute minimum value is -3, and it occurs at x equals 2. Very good. Just as an aside, that reminded me that on the AP exam, when you are asked for the absolute maximum value, make sure that you do report that value of 8 and not just x equals 7. And it's not a good idea to report an ordered pair like 7, 8. If it asks for the maximum value, darn it, report the maximum value. So finally, Curtis, in part E, I'm going to try to tie this together with part A. What I have done is I have taken these values that I created in that table. This is the green curve. That see all those points there. Those were my z's, g of z's, so my x's, g of x's, and I've connected them with a smooth curve. And so one thing that I might ask my students is, can you see any sort of relationship between these two graphs? And with a little bit of prodding, one might see that when g prime of x, which is f of x, when that is less than 0, g is decreasing. When f of x is greater than 0, g is increasing. And that might lead your students into this idea of the fundamental theorem of calculus, and that there is some sort of connection here between that function g defined as an integral and the derivative of g and f. Very cool. I like that one. It's got a lot of nice questions in there that you might see on the exam. Tom, I'm going to turn it over to you for a second for a little technology.
Okay, great. All right, let me fire up my TI-84 so you can see it. Hopefully that's coming up okay.
Got it.
All right. So this problem that Steve's been presenting, this has really been a classic one. At some form or like this has shown up on the AP exam, I think, for, gosh, like 20 years running, where students are presented the graph of a function, and it's often piecewise linear. It might have a piece of a quarter circle or semicircle, maybe a piece of parabola thrown in there, but it's presented graphically, and then you're presented with an integral function. And so you really need to know your fundamental theorem of calculus to work with that. So it's a really classic problem. It's often going to appear on the non-calculator part of the exam. Mm-hmm. That said, when teachers are discussing problems like this, they might want to do exactly what Steve mentioned, is they might want to take a piecewise linear graph or one like this and reverse engineer it. And that's what I did here. I think a little later on, I'll show a little more about the piecewise, but this is you can enter a piecewise function on the TI-84, and that's what I did here. I just kind of worked through and figured out each one of those pieces was linear or constant. I figured out the formula for each piece and then put the appropriate interval. So it was -2 between 0 and 1. And then I figured out the next piece of the graph, a formula for that, and for the interval that it was for, valid for 1 to 3, and so on. And so these are the 5 pieces of the function I came up with. And here's a graph.
Wait a minute, Tom, before you leave, would you go back and I have one quick question about that. So we had 5 pieces to this function. Is that the maximum?
I'm not sure. It certainly will do at least 5 pieces.
Yes.
Yeah, okay. I think 5 might be the maximum.
Okay. 5 is as many as you can do.
Okay. So one other quick question, Tom. I think this is a really cool feature. Is there any way to for example, on a computer screen, I can sort of grab that bottom dotted line and pull it down so that I could see all 5 pieces at once. Is there any way to do that?
Um,
No,
I'm
Steve.
not sure. Yeah, I'm not sure you
So
Okay. Okay.
no, Steve, but you can, and I actually really like to do it this way. If I'm entering a piecewise function that's more than 3 pieces, I
Yes.
actually do it on the calculator screen. Um,
Oh,
where
I
I
see.
can
Well, you can see.
where I can do the entry without having to scroll.
uh,
So
I see. So you do it on the calculator screen, and what do you do? Then assign it, store it to Y1?
right.
I
You
see.
have to do it in, you have to make it a string. So you open quotations, and then you use this same template like Tom did.
I
Enter in
see.
all of the conditions and everything, and then you can store that to a Y variable.
So that would allow you to see all 5 on the
So
screen at
that would
once.
allow you to
yeah,
see all 5 of them at
I
the same
see.
time.
Okay. All right. Thanks, Curtis.
Yeah.
yeah,
Sorry, Tom.
yeah, no problem. Yeah. Well, here's a graph of it, and it pretty much, yeah, just matches up. And in fact, you definitely, when you're doing these, if you're trying to reverse engineer them from a graph that's given to you, graph what you come up with and make sure all the pieces are lining up okay. I think something that's sometimes surprising to folks is the this fundamental theorem technique works on any function and works on the 84 also. So we can define an antiderivative for this function, an integral function in y equals. I'm just going to do that as y2. I'm going to actually define the g of x that Steve had. I'll just go to the math menu, go down there to number 9, the integral. And let's see, we're integrating from 0 to x. And then we are doing y1. I'll do of t
Okay.
with
So
respect to t.
Tom, we just got an interesting question on the multiple choice portion of the exam. Do you have a strategy for kind of looking for traditional, maybe they're distractors about the fundamental theorem of calculus to kind of help students think critically about those questions? Are there exam taking tips that you can think of? And you don't have to have one right away. Perhaps some
Yeah, I think
teachers
there's,
on here
I
might
mean, I
have
think
some
common
too.
errors would be one thing I would just alert
Sure. Yeah.
students to, because the ones that they often fall into. I think Steve's next question has some good examples of that,
Okay.
the
Okay.
fundamental theorem and the chain rule. Yeah.
Okay.
And I know somebody, was it Ryan, asked about practical applications.
You did. Yeah.
My thinking of the fundamental theorem really radically changed several years after I was teaching calculus. I mean, when I was a student, I thought, oh, fundamental theorem is cool because if you're given a definite integral, it gives you a much easier way to calculate it than the Riemann sums and limits, right? You find an antiderivative, plug in the 2 endpoints, take the difference. Well, later on, I became to appreciate where it's really cool is the other version of fundamental theorem. And that's this one that we're looking at right now. You give me any continuous function. It doesn't even have to be differentiable. This piecewise linear function's got some sharp corners, but it's continuous. So
Right.
broken. That has to be the derivative of something. And we have a single formula that will produce the antiderivative guaranteed for any continuous function. And this is it. You just set up a definite integral function using whatever lower limit you want. This one, we were given 0 as a lower limit. And this is guaranteed to be an antiderivative of my y1. Now, if in practical application, if y1 means something like velocity function, then I can manufacture the position function in an instant. Or if it's
Right.
acceleration, I can manufacture velocity. Or if it's any rate of change whatsoever,
Any rate
I
of
can
change.
recover the accumulation function with a single formula using this definite integral thing.
Right. That's great.
So let me go ahead and graph this thing. It's going to be a little bit slow because what it's doing is it's calculating a definite integral for each value. In fact, it's so slow, maybe we would want to speed it up. Let's see if we wanted to break off of that. Let's see, what could we do here?
Tom,
Yeah.
just a quick strategy since I don't see any potential for asymptotic behavior here. You can turn off the format. If you go under format and turn off detect asymptotes, that will that'll speed it up. Another way to kind of look at that is Mark suggests in the chat. You can also change the X resolution.
Yes, and that's one I was going to look at.
But detect asymptotes actually should do a pretty nice job. Try graphing it even just with
okay.
that should actually speed things up quite a bit. Well, it did at first, but even still, it's not really significantly faster even already with just that one change. Now, XRes 3 would, of course, speed it up even more, but you won't see as many points.
Yeah. Actually, I kind of like the slowness in the way is I can appreciate what's happening here. When my blue function crossed the x-axis where it changed from negative to positive, I can see the original function's got a relative minimum there. It went from decreasing to increasing. Now let's see what's going to happen at this sharp corner up here. Will we have a maximum? Well, I'm thinking not, because the function's still positive, the blue one. And so that red function should still keep going up. In fact, it's going to leave the window on me, I think. It'll eventually come down. But you can see you can graph any, even a piecewise linear function, you can do the antiderivative for. And I'll go ahead and just show one last, that other technique for speeding it up would be if you go to your window and you change XRes to 2 or 3, it will literally graph 2 or 3 times faster. And that's because you're skipping, that's every third pixel or every second pixel if you have L2. So let me graph again. And this time it should really graph fairly quickly. Oh yeah, it's gone. But you can see how it's jumping in bigger stretches there, every third pixel.
Still producing a pretty good graph, though.
It is. It's still remarkably smooth. Oh, you can see what happened, that sharp corner up here at the top.
Oh, yeah, because of the
because of the resolution.
Yeah. Yep.
And this will eventually come back down some, but it'll take a while. So
it may be off screen even still because you've accumulated.
I should have went ahead and changed my window height too. So one last thing I will show here is I'm going to go to the table. I think. Let's see, did I? Oh, let me try that again. Oh, I stopped the action on it.
You have to stop the action. You have to quit.
Okay.
Now you can go to your table.
I'll go to the table. Sorry. Thank you for this. And that may be taking a while because for the values in the table, it's having to calculate all those definite integrals.
Did you have it set at auto?
I think so. Yeah.
Okay,
so
gotcha.
It should be every integer, I think. So there we go. Now, y1 was the original function, but y2 is the one that Steve had a table for. And as I look at Steve's table, it's looking pretty good.
Yeah, how about that?
Great. All right, cool. So I think I'll turn it back over to Steve at this point. All right.
And Tom, on that table, it wasn't required, of course, that you used an integer value. We could have set that for ask, right? And put in
Right.
3.5 if we wanted to, right?
Yeah.
Okay.
Similarly, after we had graphed the integral function, we could use trace and trace over to any specific value we want to. Yeah.
Okay. All right, Curtis, here we go with number 2.
Oh man.
Oh no. Sorry. All right, so I've got a couple of problems where I'd like to see if I can find the derivative of each function. Knowing the fundamental theorem of calculus part 1, I've got a couple of common types of questions. I would say perhaps found more on the multiple choice portion of the exam. So here's g of x. How do we find the derivative of that function g? Well, let's see. We're going to use the fundamental theorem of calculus part 1, but notice that this bound, this upper bound up here is no longer just x, but rather a function of x. So in order to do this one, and I know your students are very quick at this, but in order to do this one, the way that I think about it is that there's a chain rule going on. And so I'm going to let u be equal to x squared minus 1. And I'm going to take the derivative of the outermost function and work my way inside. So I'm going to let u be equal to x squared minus 1 as I take the derivative of the outermost function times the derivative of the inner function du dx. That's just a chain rule. And let's see, the derivative of this function with respect to u, that's the fundamental theorem of calculus. That would just be this integrand evaluated at u. So it's u cosine u, again, times the derivative of u with respect to x, chain rule. And then to finish this off, I'm just going to substitute back in for my expression for u, which was x squared minus 1, I believe. And okay, I took the derivative of u with respect to x, which was 2x. I'm sure there's probably a little bit of simplification or some other ways that I could write that expression, but that's pretty good. Let's try another one. All right, how do we attack this one? This time I've got a definite integral of the sine of x to pi of the tangent inverse of t dt. So this time my function of x, and not just plain x, but is the lower bound. So in order to do this one, I've got to use a property of integrals. Remember that one, Curtis? When I flip the bounds, there's a negative sign out in front.
Right.
One of the very first properties that we learn about, once we learn about Riemann sums and about definite integrals. So this becomes the derivative of, there's a minus sign. I flip the bounds, pi, sine of x, and I won't go through this one in gory detail. We know how to do this now. We're going to use the chain rule. There's the minus sign way out in front. The derivative of the outermost function here would be the tangent inverse of the sine of x times the derivative of the inner function. The inner function is sine. So the derivative of the sine is the cosine. And I've got a dot in there just to make sure that that is the tangent inverse of the sine of x, but that whole thing times the cosine of x. Doesn't look very pretty, but I think that's the answer. And oh yeah, there's a minus sign out in front. Nice problem. Using the fundamental theorem of calculus part 1, but also a property of definite integrals that we learned about. And let's try one more here. Let's take a look at part C. This time I've got a function g of x, which has functions of x, some crazy ones here, e to the 1 over x and e to the x, and there's a log in there as the integrand. Yikes, how do you do this one? Well, once again, we're going to use a property of definite integrals here. And we're going to split this original integral up into 2 separate definite integrals. And we can choose any constant that we want, but perhaps a common one would be 0. I'm a little worried about this one because if I choose 0, I know that the log of 0 is not defined there. So it's really an improper integral, but bear with me on this one. I could use another value like 1 if I really wanted to, if that bothers some people. So here we go. In this first definite integral, this expression in x is in the lower bound. So I've got to use this property of definite integrals to flip the bounds. And there's my minus sign out in front. This one remains the same. And now I'll use the fundamental theorem of calculus together with the chain rule, and here we go. So this first expression becomes, taking the derivative, the log of that upper bound, e to the 1 over x, times the derivative of that upper bound. Have I got that right? That's the chain rule again, holy Toledo. The derivative of what's up top here, e to the 1 over x times the derivative of that, well, that's really x to the minus 1. So the derivative of that is minus 1x to the minus 2. There it is. Plus the derivative of this expression, which would be the log evaluated at that upper bound times the derivative of that upper bound, which is just e to the x. And I think there's a little bit of simplification here. Let me see if I've got all of this correct. We know that the log and the exponential, the natural log and the natural exponential function are inverse functions. So the log of e to the 1 over x is just 1 over x. There's the minus sign right there. This remains the same. I brought it down. There's a c dot in there. The log and e are inverse functions, so there's the x. And I think there's just a little bit more simplification. The minus signs cancel, become a positive. There's a 1 over x cubed in there, e to the 1 over x, xe to the x. That's kind of cool. I took the derivative of that function. The natural log is nowhere in sight in that final answer. And I did a little bit of simplification, used some properties, knowing that the log and e are inverse functions. A lot of little things going on in there. Cool. Tom, is it possible for you to do something with technology on this one?
Yeah, I think so, Steve.
Okay.
Give it a
All
shot.
right. I'm going to hand it over to you. Here we go.
Okay.
Beautiful. There we go.
So these problems you were just looking at, Steve, they're very symbolic, right? I mean, you're calculating
Right.
a symbolic derivative of a function that happens to be presented as a definite integral function with a variable limit, or maybe variables in both limits of integration. And you might think, well, gosh, I could check things like that with a CAS-enabled calculator or computer algebra system.
Yep.
But actually, you can check these things with the TI-84 easily now. I just want to illustrate that. And this would be good not just for these fundamental theorem types of questions, but basically any derivative you're doing by hand, you can check it graphically with your 84. So let's just use part A as an example here. So in Y1, I'm going to put in the function you were looking at in number 2A. And I believe that was, I'll bring up the math menu, it was a definite integral function. It was, let me get the FN int. There we go. We've got a nice integral there. I think it was, let's see, take a look, 0. And then up in the upper limit, you actually had an expression involving x. It was x squared minus 1.
Mm-hmm.
And then our integrand, I think, was t times the cosine of t. And then our variable of integration was t. Okay. So that's our kind of interesting definite integral function, but it's actually composed with another function here. So what I'm going to do is I'm actually, we could take a look at the graph of that. Well, let's take a quick look at it. Let's see, my window, I'll tell you what I'm going to do is zoom decimal, just get a quick graph.
Holy
kind of a wild one. It's really oscillating pretty wildly. I wonder if it settles down as you get closer to 0. Okay, yeah. All right. So it's pretty wild, but that's the graph of this weird function. So Steve came up with an antiderivative. I'm going to try my own antiderivative here. So I'll go to y equals. And to illustrate, what I'm going to do is make one of the common mistakes students will make. So a definite integral function like this, when students are taking the derivative, often they'll say, okay, I need to take that upper limit and just replace my variable of integration with that, okay? So I think the derivative is going to be x squared minus 1 times the cosine of x squared minus 1. Now, what's the mistake I've made here is I'm not done yet. I really need to remember the chain rule, but that's probably one of the most common errors is forgetting that the chain rule, I need to take one more factor is going to be the derivative of the x squared minus 1. So I'm going to put that in, though, and say, oh, I think I've got it. Well, how do I check my answer? Well, in y3, I'm just going to put the derivative of y1 using the numerical derivative. So I'll go to my math menu, go down there to number 8, take the derivative with respect to x of y1. Go to my vars, y vars, function, there we go. And that'll be x equal x for graphing purposes. So that's going to graph the derivative. It's not doing it symbolically, but it's using the numerical derivative, getting difference quotients over really tiny intervals. And I'm going to go ahead and turn off y1 because I just want to compare the two. My candidate for the derivative is y2. The calculator's derivative is y3. I want to see what those graphs look like. Okay, so that one was mine. And here comes, it's taking some time. It looks pretty good. Oh, I'm seeing it's starting to missed a little bit there. Do you see I shouldn't see any red if my derivative is correct. I'm figuring I should maybe took a little bit. Oh, now I'm definitely seeing some problems.
Something's wrong, huh?
Yeah, something is definitely wrong here. Yeah. Okay. So let me go. I can already tell something's wrong. So I go back to my y equals, and I might look and say, oh, I forgot my chain rule. Let me go ahead and put on an additional factor of 2x. And I'll tell you what, I'm going to look at just a little bit smaller window. Why don't I go from about -2 to 2?
Sounds good.
I just really want to compare these two graphs. Okay, so let's graph both of them again. Okay, there's my derivative. And now here comes the calculator's derivative. This time, mine's right on the money. Okay, I can see that, wow, okay, now I'm much more confident that my symbolic work is correct. Okay. And as I mentioned, I think this is a neat thing to do just for practice, thinking graphically about the derivative. Because I think a neat kind of problem is, here's a graph of a function where you have no formula at all, and you can sketch the graph of the derivative just by thinking in terms of some values. But here this was a way to catch that error, and it won't tell you exactly where the error is, but it will at least raise a red flag to you and say, hey, you need to look at this again. I won't do these with the other two parts, but I want to turn it back over to you, Steve. So
okay.
Unless there's something, Curtis, that you've seen in the chat that I should try to address while I'm.
No, I don't think so.
Okay. So back to you, Steve.
All right. Thanks, Tom. All right, number 3. All right, so I think this is kind of a cool one. This will demonstrate, I think, some interesting technology. I'm going to show you some stuff on the TI-Nspire. Tom may be able to do some of this on the 84 also. There are 2 functions here in this problem number 3. I think as we work through this, it's important to keep them straight. So here's the first one. This function f is defined piecewise. It is the sine of t divided by t almost every place. except at t equals 0, it's equal to 1. So in the top part here, you'll notice that this piece is not defined for t equal to 0, but I'm going to define it to be 1 when t is equal to 0. Now, it turns out that by doing that, and this seems kind of weird, but it turns out that by doing that, this function is now continuous for all real numbers. So I have a question in there in parentheses. Can you justify this? And that's a good question for tomorrow morning at 8 o'clock. How do you do that? How do you justify that that is in fact continuous for all reals? Well, okay, off of 0, it's fairly easy argument because I know about the sine function. I know about t. That's actually a linear function. It's actually a polynomial. So I have a quotient of a continuous function and a continuous function. So that's pretty easy. I get that. But how do you know that it's continuous at 0? So we'll leave that. It is, but we'll leave that as an open question. So here's the function that I'm really interested in. In the spirit of the fundamental theorem of calculus this evening, here's g of x defined to be the definite integral from 0 to x of f of t dt. And the very first thing I want to try to do is to sketch that graph of g. So Tom has showed you how to do this a little bit on the 84. I'm going to show you how I did this on the Nspire, which I think is really cool. You can on the Nspire, of course, also define piecewise functions. And so that's what I did right here. It's kind of hard to see, but that is an f of t right in there. And so once I've got f of t defined piecewise, I'm going to define g of x to be this definite integral from 0 to x of f of t dt. And then on another screen, on a graph screen, I'm simply going to graph that function g, and this looks pretty interesting. Seems to go through the origin. Seems like there might be some sort of symmetry in there. I'm not sure. Tom, help me. Does that look like it's symmetry about the origin almost, doesn't it?
Sure does, yeah.
Yeah, it kind of
Looks like
does.
an odd function in
Yeah.
more ways than one.
And it looks like there might even be something funny going on as x increases without bound, as x decreases without bound. I don't know why, but I sort of expected when I first graphed this function g that as x went increase without bound and decrease, that it would be going off to plus or minus infinity, but it doesn't look that way. So eventually we're going to have to resolve that. At least I'm going to have to in my mind. So at what values of x does this function g have local maximum values? I'm going to sneak back over here. Here's my graph. I apologize. Let me see if I can arrow up just a little bit. Can you see where there are local maximum values? There seem to be a ton of them, don't there? There's one. There's a local max. There's a local max there, and so forth. So without going into this in too much detail, I've got to find out, well, where is g prime of x equal to 0? Well, wait a minute. Using the fundamental theorem of calculus, g prime is sine x over x. How do we make that 0? Only when the numerator is 0. So that's where the sine of x is equal to 0. Well, where does that happen? At x equals 0, plus or minus pi, plus or minus 2 pi, and on and on and on. But where do we get a local maximum? Now you're going to think about this. If x is bigger than 0, then the sign of x has got to change from positive to negative to give me a local max, right? Because this denominator would be positive. Where x is less than 0, the sign of x has got to change from negative to positive, right? That would make the first derivative change from positive to negative and give me a local max. Got to think about that a little bit. So when I think about my unit circle, where does that happen? And I look at my x values up there, plus or minus pi, plus or minus 2 pi. Here is where my local maximums occur. I'm going to sneak back over here. So this value right here, kind of hard to see, but that's actually occurring right there at x equal to pi. And this value right over here is actually occurring at minus 2 pi. Kind of cool. So there's infinitely many local maximums and okay local minimums also. Wow. See. Find the coordinates of the first inflection point to the right of the origin on the graph of G. I like this problem because this to me seems like a typical AP calculus free response question on the calculator active portion of the exam. It seems to me as I look at that graph and I reproduce part of it over here on the right-hand side, it seems like there is a change in concavity somewhere between 0 and 7 over there. It sure looks like it. How do I find that? Well, it seems to me I really want to find the second derivative of G. Well, I've got the first derivative. How do you find the second derivative? Well, let's see. I guess I'm going to have to use the quotient rule. And I hope I've done that correctly. Now, look, I could, if I really wanted to at this point, I could, if I really wanted to, get a common denominator, which would be x squared. And I could, if I really want to, don't let me make a mistake on this one, Curtis. I could, if I really wanted to, write this as x times the cosine of x minus the sine of x, all of that divided by x squared. And then think about, well, how do I make that second derivative 0? Well, the only way to make that fraction 0 is to make the numerator 0. And so I could work with that x cosine of x sine of x. I don't think that's going to help me analytically with a piece of paper and a pencil. I still don't think I can solve that analytically, but I could work with that. It might make it a little bit easier, not sure. So what I did on a calculator page on the TI-Nspire is I took this expression for the second derivative and I asked, well, where is that 0? Now, we've talked about this before. There is a built-in solve function on the TI-Nspire. But I like to use the zeros command because I can put the results from that built-in function into a list, and then I can refer to elements in that list. So this is really cool. It says, find the zeros of that function for x, or the values of x that make that 0. And it's kind of hard to see, but there is a vertical bar in there which says such that x is between 3 and 5. How did I figure that out? Well, I looked at the graph, and it sure seemed to me from the graph that there was a point of inflection between 3 and 5. And indeed there is. So the x coordinate is 4.493. I think, if I remember correctly, I had my calculator screen here at least set on 3 digits to the right of the decimal in AP calculus mode. And I wanted to know the y coordinate, so this is really neat. I evaluated G at the first element of my zeros list. Did I say that right? I evaluated G at the first element of my zeros list. So my point of inflection is 4.493 and 1.656. That's really cool.
So
Backed
Steve,
up. Yes, sir. I'm sorry, Curtis. Go ahead.
I got a question that came in.
Okay.
Thinking about the way you approach this problem, would you do it differently if you had different trig functions involved here? I mean, you've got sine x over x. That's got a pretty nice and you know, sort of a cool thing happening there, but what if it was tan x over x, or you know, a different trig function? Is there a difference in your strategy, or kind of the same
So
thing?
one thing that I might try, if this were a calculator active problem, and probably is, Tom, back me up on this one if you would. On the TI-Nspire, I would certainly create a sketch of the graph like I have over here.
Sure.
I believe built into that is find a point of inflection. I think there's a numerical method that will find a point of inflection. So that's one thing I might try.
Sure.
Another thing I might try on the left-hand side on a calculator page is if that function g prime is more complicated. Rather than try to analytically find the derivative of that, the second derivative of g, I would put the expression in here. I would say, well, find the zeros of the derivative of that expression.
Sure.
I could use
Okay. Take
DDX.
advantage of the
Take
caps.
advantage of the built-in functions
Mhm.
on the TI-Nspire. Yeah. Yeah. So I think that would be my strategy. I guess, Curtis, because I'm old school, too, one of the things that I would want to try is, geez, can I solve this analytically? And this one I can't. So I've got to do something numeric here. I've got to do something with the calculator. That's a good question. Okay, D. All right. So do you think this graph of G has any horizontal asymptotes? Why or why not? So what the heck was going on as X increased without bound, as X decreased without bound? Well, this one I don't know if I can prove. I can show you analytically, but what I did is a little bit of numerical investigation. It looked to me like those curves were kind of zeroing in on about 1.5 and minus 1.5. And son of a gun, I created a table of values here where I put in a value for X in that first column. And in the second column, I computed the value of G. So I'm getting values for G way out to the right and way out to the left. Okay, not near infinity, but pretty far up. And look what's happening here. As X increases without bound, I sort of recognize that number. And in fact, here it is with more digits down here, if you can see it. And similar things, there's some symmetry here, as Tom and I talked about a minute ago. Boy, as X decreases without bound, it sure looks like the value of G is approaching pi over 2 to the right and minus pi over 2 to the left. That's pretty cool. And I'm not sure I can show that to you analytically, but I'm pretty sure that's the right answer. That's a neat problem.
You may have more confidence than me, Steve. I mean, it's certainly close to, but I'm not sure. I have to think about it. Yeah, no,
Yeah, I'm pretty sure that's the right answer. It is pi over 2 and minus pi over 2. Okay, so down at the bottom, I had to do one more with technology here. Not really related to the fundamental theorem of calculus, but use technology to solve this equation, g of x is equal to 1, just sort of illustrating another little bit with technology. Here's the graph of G on the left-hand side, and I also graph the horizontal line y equal 1. And I can use a built-in function here on the left-hand side on the calculator screen to find where those two graphs intersect, 1.065. And on the right-hand side, what I did is simply use that zeros command once again and find the zeros of this function g of x minus 1 between 0 and 2. And there's my 1.065. So I got the same answer. I feel pretty good about that one. Tom, anything with technology? Should I take a quick look at the last one?
Oh, go ahead and take a quick look at the last one, Steve.
Okay. So Curtis, I saw a problem like this somewhere a while ago, and I thought this was really unique. I might not get to finish all of this one here. We're pretty close to 9 o'clock on my clock. So let's just think about this one for a minute. The graph of a function f is shown in this figure, and the table lists specific values of f of x for selected values of x. So I've got some integer values there, minus 4 to 4, and I'm telling you those are the values of f. And f is actually a nice smooth curve which goes through all of those values, which, by the way, is not easy to produce. Okay. All right. So now I've got this function g defined this way. The definite integral from 0 to x of f of t squared minus t squared. A little bit different than some of those that we've looked at before. Can you find the values of x at which the local extrema of the function g occur? Holy Toledo, how do we do that? Well, if I want to find where the local extrema occur, I'm going to take a look at the critical values. So I've got to find g prime of x, and I've got to set that equal to 0. So, okay, g prime of x by the fundamental theorem of calculus is f of x squared minus x squared. I've got to set that equal to 0. So I've got to find out where the heck is f of x squared equal to x squared? So I guess I've got to find where is f of x equal to plus or minus x? And here's how I figured this out graphically. I think if I put in these lines, y equal x and y equal minus x, and find out where those intersect the graph of x. And this took a while to do, Curtis, so that it worked out nicely. It does indeed intersect this function f in several places. So let's see what's going on here. At this point where x is equal to minus 4, I have f of x equal to minus x. At this point where where x is equal to minus 3, I have f of x equal to x. At this point where x is equal to 1, I have f of x equal to minus x. At this point, I think I have f of x equal to x and f of x equal to x. And I believe at those 5 values, they're a local extrema of that function g. That's pretty cool. Now, I think I probably ought to go a little bit further, and I think I probably ought to think a little bit about, well, okay, a sign chart, just to double check here to make sure that we do indeed have local extrema there. But that's a nice problem to end on. Curtis, thank you.
Wow, it was great. That was great, Steve. We had some other good questions going on here tonight in the chat. Looking really involved in the chat tonight. I appreciate all the back and forth and the folks posting and asking questions. That was great. Thank you also to all the calculus teachers logged in and answering questions for others. That was really good. I appreciate the community aspect that's growing.
Me too, Curtis. Very cool.
I'm going to, I'll post the solutions document here. I actually am also going to post the one for the pre-calculus session from last week up on the pre-cal session. So if anybody's out there looking for those, we will get those up there. And then finally, my email is in the chat. I'm putting it in there, and if there are teachers who want to have professional learning certificates, you just email me and I will return a link for a certificate. So thanks again for everyone. We'll be back here in 2 weeks on March the, what is that? Or is it the last one still in February? I guess the last one's still in February, isn't it?
We have one in, no, the next one is in March 3rd.
March 3rd. I thought it was, yeah, I thought it was really close. I can't do the calendar in my head that fast. So yeah, March 3rd will be our next calculus session. Looking forward to that. And then we'll be back around with pre-calculus here in just a few weeks as well. So.
And Curtis, just to answer that question from the very beginning.
Oh.
I would like to suggest that to the student who asked that question, look up this function that we talked about tonight, sine of t divided by t, and look up that function associated with that integral function g of x. And I think you'll see a couple of very nice real world applications.
So that's to Ryan.
Ryan.
That sine of t divided by t.
Correct.
Function. Look that up and have a little explore.
Yes, sir.
All right.
Very good.
Thank you very much, Steve. We will talk soon.
Okay.